Welcome to new seminar. This is today a real new opening, namely a Center for Digital Science and Technology at the Cardinal Stefan Wyszyński University in Warsaw is opening its seminar. And today the seminar will be somehow specific because of honorable guest of our center, Professor Nobuyuki Kenmochi of Chiba University, honorary professor at Chiba University, who has been my personal research partner and a partner of our colleague and friend Maria Gokieli for quite a long period of time. Actually, welcome Professor Cytowski, Dean of the faculty, and we have been working together since late 80s. So it is in between more than 30 years of collaboration between mathematicians from Japan and Poland, with the outcome in form of a long series of joint conferences, symposia on applied nonlinear analysis, in particular oriented towards problems in science and industry, where we have met already nearly 10 times, concurrent, just either in Poland or in Japan. And the result of those meetings is a series of proceedings volumes and journal issues of the Journal on Advances in Applied Mathematics and its Applications. It's an international journal published in Japan, complemented by a series of monographs and proceedings in book form. Today, this is a seminar that is to summarize our most recent research that in between already has become a basis for publications that have appeared at under label of Cardinal Wyszyński University. So there are already few publications with our university affiliation. And let me just introduce you to the formula that brought us to this seminar and to future research plans. Center for Digital Science and Technology will comprise three main lines of research and development. There will be a range of activities on digital medicine and its problems. Then there will be the whole suite of activities on intelligent networked systems and their applications. And finally, there will be a special focus on fundamental research oriented towards mathematical and algorithmic foundations for advanced data analytics and data-based modeling. And since the area, the scope may sound enormous, we have focused on some specific areas of research that we believe, on one hand, belong into the category of frontier research, but also exhibit a wide range applied interest in various areas of industry, public life, most generally. The areas that we have in mind in particular address developments, processes, dynamic processes that contribute to structure formation, to development of various structures in complex systems, the kind of problems that are of wide applicability range, in particular as related to evolution of populations, as related to development of multi-component physical systems and their structure evolution. The main motivation for the study that we shall report today was an interest in generalization of mathematical methodology that would enable rigorous treatment of problems where nonlinear governing mechanisms are of coupled nature. So you have not just a single governing equation for the process described, but a system. And since the nonlinearities that are accounted for are of quite high complexity, it has been a challenge for a long time, and it was only possible due to long involvement of Professor Kenmochi into applied nonlinear functional analysis and variational methods that eventually we were able to achieve a breakthrough in handling this type of phenomena, never treatable before. In particular, you will see today models that include coupled systems describing flows, so having some Navier-Stokes'a nature with constraints, but also some other physical driving mechanisms. And this is a tremendous area for mathematical studies, because the advancement achieved so far is still in a very early stage. The range of open challenges is quite enormous, and I would be more than happy if, on one hand, keeping in mind applied interest that I would like to foster here, we would keep very strongly our eye on basic mathematical questions that are of highest current interest for mathematical community as whole. So, with this introduction, let me proceed to details. This was just about the idea, but about specific topics, I would like to ask Maria Gokieli, who is also a new person at the Cardinal Wyszyński University, to just present the basic results that have been achieved over last 3 years, more or less, and have already been reported in a form of a sequence of publications. Some of them are just now about to appear.
Thank you. So I will indeed try to summarize a piece of research that we have made together. Do not be. I know that the main interest will be this number here. I have a lot of slides, but they are very short. So, and I will try to skip these which are not essential. Let me say that I will talk about models and methods these models will be set in terms of partial differential equations somehow, but that we transform into a variational form that becomes, in our case, an inequality. This is maybe the one of the common point of these models. So do not enter maybe too much into the details of the models that I will give as examples. I will try I write them, but they are only example of some general idea and of the application of this general idea. So we will have three parts: the introductory about real phenomena, then about the modeling of these phenomena, and then about the mathematical part which leads to solution. The first example of phenomenon that has actually inspired us is the biofilm formation. So you see we have some kind of flow of, it can be liquid or it can be air, and in this flow we have some organism that attach to a surface and eventually become an obstacle to this flow. This obstacle is of course changing in time and depending on the flow itself. Yes, these are living organisms, so they are also have some nutrient they consume. We have some biological reactions inside. Okay, so this has a lot of importance in medicine because these biofilms, when in organisms like human organism, are responsible for most diseases. But also they are they have importance in industry because they are actually used as a form of control over petrol extraction. So this is a simulation that has been performed by our friend and colleague from ICM, in which you see this is actually an application to petrol. She had performed it with colleagues from the United States. So we see chains. We have a flow through a porous medium. Yes, let's think of it as soil, and this flow is transporting some living organisms that block some of the chains of this flow, which is a good thing for petrol because we would like just one place where this petrol comes out, yes, and not too many channels when it is where it is lost. Another example of phenomenon that has inspired us somehow, and it is this long work of Professor Kenmochi and Professor Niezgódka, is the Stefan problem, just phase transition between ice and water. But usually this phase transition is also coupled with a flow of water, which transports ice. And a third application, let's say, that has been also an inspiration, which has not really been put into formal terms up to now, but discussed, is biomass combustion. So we have some piece of wood that we put into this kind of oven, and we put air into it, and we proceed to combustion of this biomass, which produces energy. Yes, but actually it is also flow of air through this porous medium, which is here wood. So, how to model these? This is part 2, the longest one. How people used to try to model these phenomena, and I will first talk about classical models, which include some sharp interface. What is this sharp interface? So we have some domain. It is a domain in 3D, but I just draw it as two-dimensional, and part of it is solid, part of it is liquid, okay? And this solid part changes and liquid part changes in time. We have some interface between them on which we have to usually impose some condition so as to have a good coupling, yes, and so in terms of some variables here, for example, U can be the density of biomass, so we can consider when this density is positive, we have some solid, and when it is 0, we have liquid, in which we have some flow, which is governed by another equation and has in terms of its velocity, for example. At the same time, the same equation, for example, this is for ice. Now solid is when the temperature is negative, and the same idea here. So how we should model this kind of, we usually model this kind of phenomenon. We have, let us consider the Navier-Stokes equation for the flow, a classical model, but we have an additional condition that V is 0 in some region which can move in time, yes? So this kind of problem has never been considered in this setting. Okay, now for the biomass problem, we would have the same idea, but now we have, for example, in classical model, people consider 3 equations. One of these is this Navier-Stokes equation that we have just seen, and the others are equations responsible for biomass diffusion and some nutrient diffusion in the flow. Okay, but the idea is the same. We still have this condition that V must be 0 in some subdomain. This has been considered by these people in 2001, but this problem has never been analyzed mathematically. And the same system, let's say, for example, for the Stefan equation, we have some again, heat flow equation, and then this Navier-Stokes flow constraint on some region. I am talking about flows because it has inspired us, but we will see that other applications are also possible. So what is our approach in general is that we first relax the variable to have some continuous passing from the solid to the liquid. Then we consider this problem on a fixed domain, but we impose a time-dependent constraint. This is a function or a set which will say, okay, here our solution cannot be too big or should even be 0. And we couple these phenomena by these constraints that we impose. So this is more or less what we introduce. This is this interface. So we have some, we distinguish, let's say, some region that we consider mushy layer or interface, which is thick. What is the constraint? Okay, the constraint is some function, P, which depends on x and t, and which tells us For example, that the norm of our velocity, the absolute value, let's say, of our velocity, the norm of the vector should not be bigger than this function. So if this function, we admit that this function can be infinite on some region, then it means that we have free flow in this region where P0 is just infinite. We have no constraint. If P is 0, then we have no flow in this region. And if P is between 0 and infinite, so have any positive value, we have a constraint which will correspond to this interface. We can impose this constraint on the function itself, for example, on velocity, the norm of velocity, as I have told, or on the gradient of this velocity. This situation corresponds to a situation when we have the solid is fixed, and this situation corresponds rather to a situation when we allow the solid flow. And this shows how this function can be, let's say, simple. If we consider phenomena like this biomass formation, where actually this P this constraint will depend on another variable. Yes, so for example, actually this constraint depends on the biomass density, and it constrains the velocity of the flow. And then this function P is a function of one variable. It takes some convex form in general, monotone, decreasing or increasing, and we have these two kind of constraint that we impose on the flow velocity. Our models for the example problems that I have shown in the beginning. So our formulation, our setting, is that we take our, for example, Navier-Stokes'a equation, and we add our constraints. Simple idea. The same for the biomass system, or for the Stefan problem coupled with the Navier-Stokes'a equation. For the moment, we just impose the constraint additionally. We also can apply this for reaction diffusion systems, for example, when the diffusivity here of the chemicals can depend on what happens with, for example, we have two chemical reactions, but the speed of one reaction depends on the other reaction. Yes, so and this is the same idea more or less. And we also and this imposes a constraint on our system. So, mathematical tools and results that we obtain. Let me start from the example just to say how we set the problem mathematically. So again, example 1, we just have the Navier-Stokes'a equation. We, let's say, translate our constraint into a problem that we look for solution in some convex set. As this constraint had convex properties, we get a convex, this should actually not be U, but just X and T. We get a convex constraint on the solution V that we are looking for. And we consider this convex set as a subset of some Hilbert space in which we consider our problem. So when we pass to the variational formulation of our equation, as we have a convex set in which we look for our solution, our formulation will be a variational inequality, not variational equation, but variational inequality. I will not write the other examples because they would be long, but I state the general abstract formulation of any of these problems. This is a kind of, let's say, mathematical notation, which means in which this function psi depends on the specific equation that we are considering. This nonlinear term f also corresponds to our specific problem, and all this equation is considered in some Banach space, reflexive, and in general this space is chosen so that this formulation is as weak as possible, let's say. So we do not want to impose too much regularity on the solution. This is the general idea of variational formulations, to avoid imposing too much regularity on the solutions. And this function psi also includes our constraint somehow in this setting. This is just a formal notation.
Excuse me, please.
Yes.
Could you comment on the line at the very bottom of the slide? I'm a little bit concerned about the notation. Could you comment on the inequality?
The inequality here. Yes, I am just saying it in the next slide. Yes, we have here here we have an inclusion. Yes, this inclusion means that we are considering here. This is still formal things that this operator is multi-valued. This multi-valued operator, also the time derivative here, actually we consider it as an operator which is multi-valued, and this translates into normal mathematics as an inequality. Let's put it like this, and here I write this inequality for this. So this by definition is such an inequality. Where we have, let's put it like this. Here we have put some of the, you see here we do not expect V, our solution, to have a time derivative. We pass this time derivative on the test function. And this also makes appear this inequality here, and also this sub-differentiation means that we have an inequality. This is a classical idea actually of variational inequalities. When we have an equation and a convex set constraint, then the variational formulation becomes an inequality, and this is just, let's say, a notation for this inequality.
With initial data included.
Yes, we have here, initial data actually. This initial data is, in this abstract form, part of this time derivative operator, let's say. So, example how it really writes. This is the variational inequality that we get for the Navier-Stokes problem. Actually, this is already Navier-Stokes, but coupled with some variable u, which is responsible for this solid region. But it could be general as well. So the way we are treating this problem is that we approximate it. We approximate our constraint function so as not to have 0 and not to have infinity, and we approach our possibly the functions that appear in other equations. This is the beta function, which is responsible for the biomass diffusion, for example, so as not to have degeneracy. And then we applied, let's say, known mathematics. We formulate this problem again as a variational inequality, but with this parameter mu. And then we applied known mathematics plus some kind of fixed point theorem to obtain an approximated solution. Then we are concerned with convergence of this approximate solution because we have this parameter mu, and we want to pass to the limit with this mu going to 0. And this is the result, more or less, that I also state in abstract form, but for the Navier-Stokes'a problem. Our solutions with the parameter mu converge in some sense to a function. Now the usual question that people from PDEs know is, does this limit function really satisfies our original limit problem? This is the main part, really, which is the hard work. And this is done by compacity method, and the unusual thing that we have found here, that we used for this compacity the BV estimates. BV is bounded variation. It is a space of function which is weaker than time differentiable function. So it is with respect to time. We look not at the derivative of V, but on the variation of V. The variation is, let's say, measuring jumps, and these jumps should not be too big. And we find that we can find an estimate on this total variation, which allows us to pass to the limit. Because this space of, well, maybe Professor Kenmochi will still comment on this shortly. And so, let's say the result is that the limit function satisfies the original problem. I put here a small epsilon because sometimes we still have some averaging in space with this parameter epsilon, but it actually should not be there. And this original problem can be the Navier-Stokes'a, any of the examples that I have cited up to now, yes? And what we obtain, what was our aim, is that really our solution is 0 in the solid phase. So this is the BV estimate that, let's say, we also obtain on the solution, and actually we have before obtained it. This is in two settings, either for the gradient constraint or on the normal constraint. Yes, you remember that we can impose this constraint in the different ways. And the proof relies on establishing a similar uniform BV estimate on this approximate solution, which allows us to, by compacity, to pass to the limit in the equation. And this will be still commented by Professor Kenmochi shortly. These are the references, our works that we have published already or not yet. And this is just the example to illustrate that Professor Niezgódka was right, saying that we have already Cardinal Stefan Waszyński affiliation on our works. Thank you.
Just to continue, we shall pass to some more general comments by Professor Kenmochi, but let me just explain you why such a fast overview. The issue is that over the last several decades, the advances in treating free boundary problems by variational methods have been limited to single governing equations. So either you had flow or you treated a different type of driving mechanisms. But there are quite substantial problems where you have to combine both. And until very recently, there has been no single complete result that would enable simultaneous treatment of these coupled systems. So what we have outlined today is the very beginning, it's the very first suite of results enabling handling of variational problems coupled with some free boundary evolution. And since all of this study has originated from long-lasting research of Professor Kenmochi, I would like to ask him to make some general comments on the problems that we have addressed and on the relevance of the results that have been achieved. Nobuyuki, may I please join me? Yeah.
Do you prefer only one slide here?
Yes, I
about
have
this.
Okay.
So there is still this last slide.
Oh yeah. This one.
Well, Nobuyuki, here.
Yeah.
Yeah.
Let me mention a little bit more mathematically description. All the results which are mentioned by Maria Gokieli, their essential parts are based on the quite recently remarkable development in the theory of variational inequality. And exactly this is a new compactness theorem for parabolic variational inequality. Everybody knows very well the compactness theorem due to Aubin and Lyons. That's just for nonlinear evolution equations, not for inequality. So this is the very difficult point to overcome. But by our new result, the enable us to apply directly the compact method for variational inequality too. And you know, when we are going to treat such a kind of complicated system, for instance, first of all, we propose regular approximate problems, just like Maria Gokieli mentioned. And usually, regular approximate problem can be handled very well in the Relay-Schauder type approach. Also, we propose at the same time a procedure about the construction of the solution. Okay, so usually but the crucial step is how to show, how to prove the strong convergence of the approximate problem. For instance, you consider the Navier-Stokes'a variational inequality. How to prove the convergence of nonlinear convection term. The Navier-Stokes'a equation case, it's okay. On account of Auburn's compactness theorem, ensured the strong convergence, for instance, L2 space. But variational inequalities case, Auburn's compactness doesn't work. In such a case, in order to perform the classical Relay-Schauder principle, we need the quite new type of compactness theorems for variational inequalities. This is exactly the one we developed in our collaboration team last year. By this compactness theorem, almost all variational inequality, which Maria Gokieli mentioned, and by this abstract compactness theorem, our problem is reformulated in an abstract, very general abstract setup. It's very, I think this is very nice advanced technology. Thank you very much.
Okay. So just to conclude, to make it explicit, the approximate formulations that we have introduced undergo more or less well-known computational approaches. So you can directly implement various types of computational algorithms to find solutions of those approximate problems. You have appropriate theory enabling you to claim that solutions of those approximate problems have desired properties. But the issue is that these new results open a broad field of problems non-treatable before. There was no satisfactory mathematical framework for handling such a wide class of variational problems. Here, what we just outlined was to give you few specific examples of what might be concrete applications of this theory. But you have these two lines of arguments. On one hand, you have a range of studies addressing specific applied problems of applied relevance. At the same time, you have a general theory that covers all of these problems in a unified framework. And this is what we just wanted to introduce here, to indicate this as a new, fascinating field for mathematical research, equally interesting for people who have preference in analysis of those variational setups, but also extremely interesting for approximate numerical treatment and for computer simulation studies, as they originate from real physical problems or technological problems. Thank you very much for your attention, and if you have any questions, we are eager to answer them.
Okay, encouraged enough. It seems to me that your results can be applied to modeling blood flow in human bodies, and especially in modeling heart strokes. Am I right?
Well, Maria just mentioned an example of healing.
With the objection that we usually do not it is not completely, let's say, proper to model blood as a Newtonian fluid, but it is anyway.
It's commonly done.
It's commonly done. So yes, it is. It is. This is. I did not really mention it, but yes. The second objection may be that we should also then consider many chemical, biological reactions which are coupled to this flow, and do it very carefully.
So to call this study really originating from real applications would require to go deeply into the very nature of physiological processes related to blood flows, whereas conceptually it is nothing else but biofilm development.
Exactly, looks so.
Yes.
Thank you so much.
Any other questions or comments? So I should express our thanks for your patience and interest in coming to our introductory presentation. And I would like to invite all of you, those who participate in this seminar, but also everybody who might find these topics stimulating and interesting, as the entire presentation will be available in video form on the web page of CNT Center. So the complete presentation will be available within very few days from our web page. And just let me use this opportunity to inform you that the web page of our center has been introduced and is available under cnt.uksw.edu.pl. So you will find some more information about our scope, our plans, and our collaborative attitude, open to everybody, because the essence of our program is to build collaborations. We very badly need collaborations from mathematicians of various profile, computer algorithm people who would go into optimization of the algorithm, because these problems are of tremendous computational complexity and challenging nature, because also of one factor that we hardly address today. It's the complexity of the geometry and topology of the domains involved. So all of these create a very broad field for research, equally interesting for people who just are motivated by applications, but also this is a very high challenge to those who are interested in just mathematical beauty of the problems. Thank you very much.